Hello and welcome to the second lesson in hydraulics and pneumatics. In today's topic, we're looking at pressure, specifically pressure. In the learning goal, I want you to be able to identify the factors that affect pressure in a static fluid. So again, there's a couple definitions that we need to talk about. The altimeter, what is it? It's an object that uses atmospheric pressure to determine altitude, so it will measure your altitude. Static pressure head is the height of fluid in a column above a specific position. And I'm going to talk about those in their actual application here down below. So the first application or the item I want to talk about is a barometer. Okay, and a barometer is an instrument that measures atmospheric pressure. Now, last day we said atmospheric pressure was 101.3 kilopascals, and that's in normal conditions. All right, so in normal conditions. And what will happen during storm systems, you'll hear on the news, weather will create high or low fronts. And what that does is that's what brings in our turbulent weather, either being rain or snow. So that 101.3 kilopascals is plus or minus, say, 1.5 kPa, indicates we have what type of storm or how severe the storm, whether we have a high or a low front. So if we have a high pressure front coming through, it means that the atmospheric pressure will be greater than 101. If it's a low front coming in, it will decrease the pressure. All right? So a barometer measures that, and then you can see over here in the diagram, the barometer works with mercury in it, and mercury they use is because it's 13.6 times that of water, so it's a very, very dense liquid. And this is an example of static pressure head right here. So that distance right there is your static pressure head. Okay, so the static pressure head is a measurement above the water surface. So here's your liquid surface, I should say, and that's that measurement right there. So that's your static head. All right, we use mercury because it's more dense and it won't rise up as high. If we were using water, then we would need a tube that is very, very long because the water would move up significantly high. Whereas mercury, because it's more dense, takes more work to push it up the tube. It's a little nicer because the tube doesn't have to be nearly as long. Now the other application, or the other one, is the aneroid barometer. And it's an instrument that measures atmospheric pressure without using mercury. And that's pretty important because mercury is actually fairly toxic. In the good old days, back in probably your grandparents' days, they would handle the mercury with their hands, and what later was found out, mercury poison stems from that. It's a very dangerous substance. So the less mercury we have in the house, the much better it is. So this works with a sealed rubber tube, which is sensitive to pressure. So it works in much the same way, except we have that sensitive sealed rubber tube, or it can be a type of metal can as well. But it's sensitive to pressure and works the same way. And instead of having static head, it has a gauge to read from for atmospheric pressure. Okay, so those are two instruments we use to measure the pressure around us. Now, I want to talk about atmospheric pressure here. So what I have here is a funky looking tube. All right, so we'll call it that. Funky looking tube. So what's going to happen is I'm going to fill this tube with water. So I'm going to pour water in. So it's going to fill with water. I'm going to fill it to this level right here. All right. So the first tube gets filled up. Put the water in here. My question is, how high does the water rise in the other three tubes? And hopefully what you're thinking to yourself is that you're going to say that it doesn't really matter the shape of the tube. The water level will be the same in all three. Because it doesn't matter the shape of the tube, water will rise to the same height. So we don't have to have a wide pipe like the first one here. We can use a nice narrow pipe, which is easier to handle, in order to determine the pressure. So that's a property of liquids and air pressure. They will always rise to the exact same static head height. Okay? So measuring gauge pressure here. So again, a couple of definitions here. The first one is absolute pressure. And absolute pressure is the true pressure or sum of atmospheric and gauge pressure. So let's talk about that for 1 second. Gauge pressure is the difference between absolute pressure and atmospheric pressure. So they're all linked together here in terms of what we're actually looking at. So the formula for this would be our gauge pressure. So PG, oops, I don't know why I used rho. So P with a subscript G equals your absolute pressure, P absolute, minus your atmospheric pressure, or ATM. All right? So think of it this way. Your air tire gauge is a perfect example. When you read your air tire gauge, most of you will read this in imperial, pounds pressure. It's actually reading your gauge pressure. Okay? So in the next slide here, I'm going to give you an example of what that means. But before we move on, I have one more definition here. All right, and a manometer is an instrument to gauge pressure, and we just know this as the tire pressure gauge is what we really call it, but it's actually called a manometer. All right. Now I want to talk about this formula. You'll want to put on the formula sheet for yourself. And the definitions are right there. ATM is your atmospheric, and I've got an example right here. So if you inflate your car tire, and I'm going to use pounds per inch squared because that's what all the tires have. When you look on the tires, they're produced or created in the United States. It's an imperial system. It's one of our funny things in Canada. We really have that dual system. But car tire, roughly supposed to be inflated to 35 psi, pounds per square inch. That is the same as kilopascals. All right, so here's our rough conversion here. So do they want you to inflate it to 35 psi in total? Actually, what's going on here is that gauge pressure is equal to your absolute pressure. So I'm just using the formula from this page right here. So ABS minus atmospheric pressure. So what's happening is that the 35 is what you're reading on the gauge. So you read on gauge. The way your gauge is calculating is your absolute pressure minus the 14.7. So it's doing a conversion here. All right. So absolute. This is just your atmospheric, so that's 101.3. I have it up there on your left there. Atmospheric. So the actual pressure acting on this tire, if we rearrange this equation, P absolute would equal, and we add 14.7 to both sides, the absolute pressure is 49.7 psi. Okay? So the gauge pressure removes the atmospheric pressure. So your tire has, when you put a new tire on, it has 14.7 psi or 101.3 just sitting there. Okay? That's just atmospheric pressure. What we're doing is we're adding an additional 35 psi. So we're going to push that tire pressure above atmospheric, and that's what you're essentially doing there. All right? So that is your gauge pressure, absolute pressure, and atmospheric, and that's how that works. All right? Moving along. Pressure in liquids. Pressure in liquids comes from this formula. So this is gauge pressure again. So where PG, that's your gauge pressure, and we calculate it with multiplying D, which is your density of liquid. Your H, which would be the depth or height of your liquid. Oops, liquid. And finally, small g is our gravity, which is your 9.81 meters per second squared from earlier. Okay, so there is your formula to calculate gauge pressure underwater. So now we're looking, underwater, in oil, etc., etc. So let's talk about dams. Okay, I'm going to combine an example with a real-life application. So if you ever get to see, the Hoover Dam or any of the larger dams out there, what you'll see is a dam that's designed like this. So this would be the top of the dam. It would then look like this. All right. Base is much wider. Okay, so why is this base so much wider? Well, if we put water up behind this dam, so let's put water, and we'll take 0 meters deep. Maybe I'll change color here. So let's go surface, 0 meters. Let's say it's 10 meters deep and 20 meters deep. Okay, so the water against this dam is about 20 meters deep. Well, I know at 0 meters, gauge pressure is going to be 0 kilopascals, okay, because the depth is 0. So technically, what's happening at that depth, it's not really 0 kilopascals, it's absolute, I'll put this in brackets, is 101.3 kilopascals, but we're only looking at gauge pressure, how much additional pressure is acting on the dam. What about at 10 meters? So we go 10 meters deep in water. Our formula for gauge pressure, again, was DHG. Density of water. Water is our standard measure, so it's kind of nice. It's 1,000 kilograms per meter cubed. We're now at 10 meters, and we're at 9.81 meters per second squared. When we do that calculation, we find that the pressure is 98,100 pascals, or 98.1 kilopascals. And then if we go down to the 20 meter mark, again, oops, that one, DHG, 1,000 kilograms per meter cubed for water. We're now at 20, 9.81. So we're going to multiply or double that previous answer. We're now at 196,200 pascals, or 196.2 kPa. So as you go deeper, the pressure increases on the dam. So we make that base of the dam much, much thicker because it has to withstand a lot more pressure acting on it. So if I was to draw a pressure diagram on my dam, what would happen is the pressure acting on the dam, those arrows are going to get larger and larger because we're drawing vectors here as we go to the bottom of the dam. So your pressure diagram is a triangle, so it looks like that. That's what your pressure would look like. The arrows will get larger and larger. So in order to combat or counteract that, we have to make that base of the dam much, much thicker. So there's some examples of the pressure gauge calculations with liquid, dealing with depth. This is combining with the real-world application. If you look at dams, like I said, if you look at the Hoover Dam, if you have an opportunity ever to go there, or you look at any dam of any size, and you look down, you'll find that the base is always much, much thicker, and that's the why. The deeper you go, the more pressure is acting on that dam. All right? Good luck. Any questions? You know where to find me.